Hi, and welcome to another video on weather radar. This is our third video on the radar equation. We saw that things are getting pretty complicated before when we started talking about the different types of scattering, whether it be Rayleigh scattering or scattering or optical scattering. We figured that most hydrometeors in the atmosphere, most raindrops and cloud droplets fall in the Rayleigh scattering, so we'll use Rayleigh scattering. Things kind of get complicated when particles get really big. We're talking big hailstones. They start to kind of scatter a little bit funny, what we call scattering, where it's not really linear, it's kind of a wave. So we're going to stick with our Rayleigh scattering, assume that everything scatters based on Rayleigh scattering. And now what we're going to do with the radar equation is sum up all of the cloud droplets that are in the cloud in a volume and try and figure out the scattering that results from that. So as you know, of course, clouds contain a lot of different size droplets, big drops, small drops. So you've got a size distribution in a given volume of cloud. So we're going to say that our backscattering cross-sectional area is sigma, and the total scattering that results from the droplets depends upon all the different sizes of the droplets and how they scatter, times the volume. In other words, the number of particles and their sizes, sum those all up in that volume, in that given volume, and that'll give you your total scattering. It's kind of complicated when you start looking at the volume of a radar beam, because it's not square, it's not rectangular, it's not a box, but it's a kind of a beam that expands as you move farther away from the radar. So it also depends upon your pulse length. Shorter pulse length, you have a smaller volume. Longer pulse length, you have a bigger volume. So you have to figure out the pulse length, you have to figure out the beam, both the vertical width and the horizontal width. And it looks kind of complicated, but it's math and it can be done. It's geometry and we can figure it out. So there's the equation for the volume of a radar pulse. So what we need to do is we need to multiply that volume times the backscattering cross-sectional coefficient per unit volume. In other words, figure out all of the droplets and they're kind of sum them up in all their sizes and figure out the total scattering that results from that. So that's what we're going to do next. We're going to look at all of the scattering. So before we do that, let's kind of step back and take a look at our new radar equation. This is the new radar equation, taking everything that we've done before and sticking the scattering, the backscattering. Before we had just a simple area of scattering or reflectivity. Now it's a little bit complicated because we have the volume that we're looking at of the radar beam. And now what we need to do is we need to estimate the scattering that's resulting from all of those droplets in that volume. And we said it's going to be Rayleigh scattering because we're assuming that the droplets are small enough that they scatter in the Rayleigh regime. And we said that that was a pretty good estimate. That means that the droplets are smaller than 10 millimeters. And for the most part, that's true. We have raindrops that are smaller than 10 millimeters in diameter. So we're going to use the backscatter cross-sectional area equation for Rayleigh scattering. It's kind of complicated. It's down the bottom. It's got pi raised to the 5th. It's got the diameter of the droplet raised to the 6th power, and it's got the wavelength raised to the 4th power in the bottom. We've got this k now, k raised to the 2nd power. So what exactly is k? K is the index of refraction of the material. Depends upon what the droplet or the hailstone is made of. Is it made of ice? Is it made of water? Is water on the outside and ice in the center? So that also is kind of complicated. But we kind of simplify that by assuming that everything is water. We're going to assume everything is water in our calculations because we're not sure what it's made of. And we'll just get a kind of a ballpark figure of what the reflectivity is. So we've just kind of gotten to the end of our radar equation. One more step, and that's to combine everything, and then we'll look at the radar reflectivity and the power returned.